Okay, so greetings everyone. This is Dr. Bankole Ojo Olufunsho Samuel. So I'll be taking this class on quantum chemistry. Yes. So I initially discussed with you that we will be looking through some questions, be working this on these problems to get some solutions as a fast way to breeze through this course. That is because we don't have enough time to go deep into the principles of quantum chemistry uh, anymore. But all the same, as we take on these questions, I'm sure you will get some of the important knowledge you need to at least have a good understanding of what quantum chemistry is. I believe Dr. Akonde has done a very good job so far. So I'll just stick to my part as much as possible. Okay, so now yes, we move on to the subject matter at hand. CHM 403, that is quantum chemistry. So we are going to be dealing with 15 questions here. My initial agreement with you was 30 questions, but because of time, I have reduced it to 15 questions. Try to work and practice all these solutions. So make sure you do all of them, and I mean all of them. Okay, so you need to find time. I will deliberately withhold the I will withhold the material from you. So if you need to write, please watch the video and put down something, okay, so that you'll be able to study on your own. So it's going to be a very concise uh, class. So I'll try to be as concise as possible. That is, I'll try to save time, and at the same time, I also try to be direct. Okay. Now, question one. We are looking at the double slit experiment. Okay. So this is question one. The double slit experiment shows that the act of measurement changes the outcome. Discuss what this implies about the nature of reality at the quantum level. So I'll start with a short video. So even though I've explained this in class already, but for those that did not attend the class, as many of it refused to come around or couldn't come around. So I'll explain. This video should give you a short explanation. I hope you understand what it's saying. Kindly listen.
When a laser emits beams of light particles called photons at a screen with two slits, you'd expect to see two strips to correspond with the two slits. Instead, we see a pattern of light and dark bands. This suggests that light behaves like waves that pass through both slits simultaneously, interfering with each other to create the pattern on the second screen. However, when scientists used a measuring device to observe the slit that each photon passed through, the interference
Okay, so that is very clear, but I'll give you a brief explanation of what this means. Okay, so basically we are looking at, so here in the video they talked about light, but we will be looking at electrons. Okay, when you shoot the electrons through the double slit, okay, that's you have a space, you expect to see two patterns, but you're going to see get five for electrons. Okay, and the reason is because the electrons behave like waves, but when they behave as particle, but they behave as waves. Okay, that is without observation, or once you put a detector there. Okay, once you observe, you're observing to know which slit the electrons pass through. Then a strange thing happens. The pattern becomes just two. So you get two when you're observing, and you get five when you are not observing. Okay, so this tells us that now this now makes sense. The question says that the double slit experiment shows that the act of measurement changes the outcome. Okay, so when you are not measuring, okay, you get five, but once you are measuring or you're observing or you're detecting, you get two. Okay, so discuss what this implies about the nature of reality at the quantum level. So if you're going to answer this question, this is how you're going to approach it. The double slit experiment demonstrates the fundamental quantum behavior of particles. Okay, so we are looking at the fundamental quantum behavior of particles. Now, when a beam of particles, e.g. electrons or photons, is fired at a barrier with two narrow slits, a detector screen records where they land. Okay, so but if you were to do the same for that's expected classical, if the particles behave like tiny bullets, they will pass through one slit or the other and form two distinct bands on the screen. That is, if we are to use a bullet instead of an electron. Okay, so we are definitely going to get two distinct bands. Now look at this. If now you're firing an electron, okay, and it behaves like a wave, so what now? That is why we say what actually happens. Instead, an interference pattern of multiple light and dark bands appear on the screen, a signature of wave-like behavior, as if each particle passes through both slits simultaneously and interferes with itself. So what we are saying is, if you don't have to put down exactly the same thing, all you have to state here is that what actually happens, the electrons behave like wave, okay, and then form multiple bands, okay, okay, due to interference pattern. So you can see the two important things you need to talk about is interference pattern and wave-like behavior. They behave like waves, okay, form multiple bands because of an interference pattern. That's what is needed. The next, now talk about the measurement. Okay, so when scientists place a detector to observe which slit each particle goes through, the interference pattern disappears. That is, so remember, like I said, so only two bands will appear. So the most important thing here is you talking about a detector. Okay, let me highlight that. So we have a detector. So, and the important thing you also need to talk about is interference pattern disappearing. Okay, so you have an interference pattern that disappears when you put a detector, and then you also need to talk about only two bands appear. Okay, so only two bands appear. So those are the things you need to talk about in order to answer the question. Then now remember, the question is in two folds. The second one now says discuss what this implies about the nature of reality, okay, at the quantum level. So now you talk about, okay, yes, observer dependent reality. Observer dependent reality. Okay. So there you have it. I just can say that yes, the act of measurement does not merely reveal a pre-existing and all of that. Next, you can talk about the wave particle complementarity. Okay, so there you have it. Yes. Next, talk about the collapse of the wave function. Collapse of the wave function. And next, the challenge to classical realism. Challenge to classical realism. So these are the 4 points, okay, that are necessary to tell you that, okay, this has a profound impact on quantum reality. Okay, so yes, this is one of the most important experiments in science, because this upends our view of reality. That's number one. Number two, this tells us that the electrons behave both as particles and as waves. I'm telling you another way to state it. Okay. Number three, okay, so the before measurement, okay, we can describe the particle using a wave function. Okay, so this tells you that anything is possible, okay, before observation. So that's what number three is telling us. Okay, it's like a student that is yet to graduate. Okay, that's for you now in 400 level. You're yet to graduate, so we cannot we cannot give you a particular fit, like, okay, this is what you're going to do, okay, after graduation. We don't know. Okay, some of you might go on to be pharmacists, you might move on to other fields, maybe computer science. Some of you might move on to do advanced studies, you see. So all what we have now, what we can see is what we call possibilities. Okay, so it's the same thing with the wave function. So the wave function is like possibilities. Okay, so the particle has the possibility to be many things. Okay, that's what the wave function is talking about. Just like you graduating now, okay, you have the possibility to be many things. So you might not have become what you want to be yet. Okay, so that's what the wave function is about. Now, the third one is classical physics. Okay, this is a challenge to classical realism or classical physics. Okay, because this tells us that um, objects, okay, have are not only uh, dependent on their passive nature. Okay, that means they can have different natures based on observation or measurement, okay, or on detection. So things can change. Okay, there's no fixed nature of reality. So that's why it is a challenge to classical physics. So that's how to answer the question. Okay, so you don't have to say exactly what I've put down here if you understand what it is. Now let's move to question 2. What is the physical interpretation of the wave function, and what does so the wave function square represent? So how do you answer this? So you just talk about the wave function is a complex valued mathematical function. You can see it often written as, so you have the wave function RT. Okay, so this tells you that, okay, it's a probability in space. Okay, that's space R and T. So you have time, you have distance bound. So, and it encodes all possible information about the quantum system. Okay, so like what I've said, in the last class, I talked about, okay, you don't have the way when you look at the atom. Okay, it's not just about electrons revolving around the atom. It also has you have a probability. Okay, so the electrons can be different things all at once. Different things all at once, just like you in 400 level, you're about to graduate. Okay, so for now, it can be different things all at once. Okay, and that's just the nature of reality. But in some few years, okay, you start becoming something. Okay, maybe and only God knows. Okay, some of you have started becoming it. Okay, so that is what the wave function is about. Okay, it's like a probability of what is going to become. Okay, so just that initial, you can just focus on this, and that will be okay. That will be a fine way to answer the question. Okay, so that will be a fine way to answer the question. So just this is sufficient, right? Then the second part, what does the wave function square represent? So this is where you now look at this. Okay, so you need to deliver this. This is important. So what does it represent? So you now move to this. Okay, please, if you, I hope you are with your pen and paper so that you can just highlight the important aspects. Okay, so here it is. Okay, now question two. The second part of question two says, what does this wave function square represent? Remember, I told you that we no longer use orbits. Okay, instead we use orbitals, right? Yes. So what does this represent? So it represents the portion in space where you have the highest probability of finding an electron. Okay, so wherever you have the highest probability of finding an electron is what this represents. Let's use Dami as an example. Okay, let's say the governor comes around and say, I'm looking for somebody. His name is Dami. He's president of chemistry, and I want to give him a gift. Okay, and he needs to locate you as soon as possible. He just suddenly comes to the gate. Okay, the first thing they do is, let's say his number is not available. Okay, so the first thing they need to think about is where do you have the highest probability of finding Dami? Okay, and we can say, okay, maybe during the day at the laboratory. So the first thing you think of is not maybe the trajectory of Dami, is where do you have the highest probability of finding him. That is where they are going to approach first of all, and then they start looking at other options. Okay, maybe, okay, it's not at the laboratory, maybe it's going to be at the student center or something. Okay, or at the department. So that is how you also approach the electron. Okay, the electron is about probability. This wave function square talks about probability. Okay, it is where, so the wave function square is the probability density. Okay, and more precisely, it talks about where you have the highest probability of finding the electron. I don't know, but you can put this down. Okay, so this is a real and non-negative number. So that is it. So of course, once you square something, it becomes non-negative, right, from your basic mathematics. Okay, so I'll stop this class now so that I can move on to the next question. Okay. Yes. So kindly put down something so that you can read on your own.